So welcome to CCNP Route. In this particular topic, we're going to be talking about the EIGRP fundamentals. EIGRP is a protocol that's used quite heavily, that was developed originally by Cisco, and it's a very good routing protocol. So we're going to learn all about EIGRP, how it functions, the dynamics of EIGRP, the data structures, the algorithms, and so on. EIGRP was released in 1992 as a Cisco proprietary routing protocol. In 2013, Cisco actually released EIGRP as an open standard and while they maintain the overall control of the protocol, it is now considered to be also an IETF open standard. So Cisco's released that so that other vendors may choose to use this protocol on their platform. EIGRP is defined as an advanced distance vector routing protocol. Now, traditionally, routing protocols were distance vector. RIP being one of the very first routing protocols that was developed was the distance vector protocol. And if you've ever studied routing protocols, you've probably heard that distance vector routing protocols aren't really that efficient. They're certainly not as efficient as maybe, say, a link state routing protocol. The same cannot be said for EIGRP, however, because EIGRP employs distance vector algorithms at its core, but it also makes use of a lot of link state properties that make the protocol much more efficient, much more scalable, and much more usable in a modern network. So even though EIGRP is defined as a distance vector protocol, fundamentally it is a distance vector routing protocol. It does have a lot of enhancements, and we'll talk about those enhancements as we go through our discussions of EIGRP. Now, because it is a distance vector routing protocol, it still employs the use of things like split horizon for loop avoidance and other mechanisms that traditional distance vector protocols will employ, but overall the protocol is very efficient. We're going to learn about the dual algorithm, the diffuse update algorithm, which is the algorithm that EIGRP uses to essentially calculate the routes that go into the forwarding information base or the routing table. And that diffusing update algorithm has very specific features and functions. We're going to learn all about that in this chapter, understand all the terms that EIGRP employs as part of or utilizes as part of the EIGRP construct. And we're going to learn about all the EIGRP variables and all the EIGRP components. Most of those components are part of this dual algorithm. Things like successor and feasible successor, advertised or reported distance, and so on. EIGRP as a distance vector routing protocol has to deal with loops differently than, say, a link state routing protocol does. Link state routing protocols have a much more broad picture, or a much more detailed picture, of the topology. So link state routing protocols have the ability to make better decisions on path selection and even redundant path selection in the network. So EIGRP, trying to gain some of those efficiencies, has implemented some features to add that enhancement to it as a distance vector routing protocol, making it much more efficient than, say, RIP or even IGRP, its predecessor. That loop-free classless routing process includes things like defining a successor route, and then based on the variables and the values for that successor route, defining something called a feasible successor route. The feasible successor being the secondary path in the event that the primary path fails. We are limited to how we define that feasible successor. There is a set of criteria that need to be met before that route can be considered a feasible successor. And all of that is part of this 100% loop-free classless routing algorithm that EIGRP provides. EIGRP is an IP-based protocol. It sits on top of IP using protocol number 88. There are no TCP or UDP components to EIGRP. So in order to gain some of the reliability and functionality mechanisms that TCP might deliver for a standard application, EIGRP employs the use of a protocol called the Reliable Transport Protocol, or RTP. Now, we don't get into a lot of detail about what RTP does in this particular course. but we will look at some tables and some outputs to indicate how RTP is evaluating a specific relationship with a neighbor or a path to a destination. But RTP is used for things like sequencing, acknowledgements, those kinds of things that you would expect to get from, say, like a transport layer protocol like TCP. This allows EIGRP to provide some sort of delivery guarantee for EIGRP packets, particularly things like routing updates and queries and replies, and so on. Now, traditional distance vector routing protocols didn't handle routing updates very efficiently. In fact, traditional distance vector routing protocols like RIP would simply broadcast or multicast out all of their routes to anybody that they were attached to or any neighbor that they had, and it would identify everything in its routing table in that routing update, as part of that routing update. Now, we know from discussions in other classes that when a router needs to make a change to a table or a database, the only thing the router should be really concerned with is what has changed as opposed to the things that haven't changed. And oftentimes we can add efficiencies to our protocols by only disseminating the information that's changed as opposed to what hasn't changed. So that's what EIGRP does by default. EIGRP sends partial bounded updates, meaning that the routing protocol only advertises the changes that occur, and on top of that, it only advertises those changes to the neighbors that need to hear the information, making EIGRP in its update process very efficient. EIGRP is also one of the only routing protocols that actually supports equal cost and unequal cost load balancing. Now, we can do unequal cost load balancing in other routing protocols if we make the paths appear to be equal by manipulating metric values or interface configurations. EIGRP doesn't require that. EIGRP can, by utilizing something called variance, can actually load balance across paths that have different metrics attached to them. We would see those routes in the routing table with different feasible distances, or metrics in this case, and those paths would be used equally. So EIGRP might send 80% of the traffic over one path, 20% of the traffic over another path, depending on the overall makeup of the paths that are participating in the load balancing process. So EIGRP has quite a bit of functionality built into it. Again, it's called a distance vector routing protocol, but it's really a hybrid protocol because it does incorporate a lot of the link state characteristics that you would see in, say, OSPF or ISIS. Now, EIGRP is a classless routing protocol. That means it supports subnetting and classless interdomain routing. Most of our modern protocols are going to perform this way because it's very important that in a modern network that these protocols support subnets, because in IPv4 and even in IPv6 we do subnetting quite a bit. The default nature of EIGRP is to act classfully through the auto-summarization process that EIGRP uses initially. However, fundamentally, EIGRP is a classless routing protocol, which means that it sends the subnet mask information along with the routing updates so that the receiving router can understand the makeup of that particular network. This is very important in an enterprise network because not all of our networks have the same characteristics or have the same need. So it's important that we identify kind of the difference between those networks by utilizing a subnet mask. Additionally, EIGRP uses a very complex metric. Now, metrics are a way for a routing protocol to evaluate a certain path. I guess for lack of a better term, it could be defined as cost. I don't particularly like to use cost as a definition for a metric because OSPF actually uses a metric called cost, so it could be a little bit confusing. But a metric is really just simply a way to identify or evaluate a particular path. If it costs you less, in other words, the metric is lower, that's typically going to be a preferred path. Now, protocols like RIP use hop count as a metric. OSPF uses a relation to bandwidth 10 to the 7th divided by the link bandwidth in bits per second. So, or excuse me, 10 to the 8th divided by link bandwidth in bits per second. So we do see bandwidth come into play in some metrics, but every routing protocol uses its own metric. EIGRP uses a very complex metric. We can see the formula on the screen there representing the different components of the metric as it's represented in EIGRP. Now, along with this complex composite metric are these things called K-values or metric weights. K1, K2, K3, K4, and K5. We're going to learn more about these K-values and how these come into play in the metric as we go through the section on the metrics later on, but the K-values are a way for us to kind of place a weight or place some sort of value on the individual components that are being analyzed for a particular circuit path. For example, bandwidth. If I want bandwidth to be a major portion of the metric, or I want it to be a larger portion of my metric, then I'm going to increase the K value represented to bandwidth, which is K1, and so on. So I don't want to get into the details of the metric just yet, because we're going to have a whole section dedicated to understanding the metric in EIGRP. Now, EIGRP also uses messages to convey information and to maintain an EIGRP routing domain. More specifically, there are 5 message types used in EIGRP. The hello packet, which is used to discover and maintain neighbor relationships. An acknowledgement, which is used to acknowledge certain types of EIGRP packets. An update, which is used to disseminate routing information to my neighbors. A query, which is used to discover or learn new information for a route if the primary route fails and there is no feasible successor. So that query process is rather involved. We'll talk about that in another chapter. And then we've got the reply process. The reply is just simply a packet that's specifically designed as a response to a query. So a query, I'm requesting information from you as a neighbor. Reply is I'm receiving that information back through the reply process from the neighbor. Okay, so there are 5 packet types that we use to manage an EIGRP autonomous system, and we're going to understand in detail what each of these packet types do, how these packet headers are formatted, and the overall process involved in the use of each of these particular packet types. Let's talk about the hello packet first. Now, hello packets are very fundamental to the operation of EIGRP. Without a hello packet, EIGRP wouldn't work. That's because before anything can be exchanged between EIGRP routers, they have to establish an adjacency. Now, they establish and maintain this adjacency through the use of a hello packet. Hello packets have a very specific format, and they identify certain aspects of the neighbor: hold time, hello timer, autonomous system number, router ID, etc. These hello packets are used to form and maintain those neighbor adjacencies, so they're very important components of EIGRP. Now in IPv4, these hello packets are sent to a multicast group address, EIGRP specific multicast group address of 224.0.0.10. Some cases, hello packets are converted to unicast, but in some cases they maintain themselves as multicast packets being sent over, say, a multi-access network. In IPv6, we use the multicast address of FFO2:A to disseminate hello packet information from one router to the other. Now, these hello packets are sent unreliably, meaning that there's no acknowledgement for hello. I essentially acknowledge a hello with another hello. I send you a hello, I expect to get a hello back from you within a certain period of time. And that's really essentially how we identify and kind of acknowledge these hello packets with other hello packets.